In this video here, we're going to take a look at the division algorithm. Now in this chapter then on number theory, what we're going to focus on in particular is the system of integers. So I'm hoping you're already familiar with this notation here, but just in case you're not then, this funny looking Z here is what we use to represent these sets of integers, right? And don't forget then that these sets of integers here just encompasses all positive and negative whole numbers. And we're also going to focus then on the system of natural numbers. And again, I'm hoping that you're already familiar with this notation here, but just in case you've never seen this before, this funny looking N here is what we use to represent these sets of natural numbers. So for example then, 1, 2, 3, 4, 5, so on and so on. So the difference here then is that these sets of natural numbers just encompasses all positive whole numbers, okay? So we don't include the negatives, that is for these sets of integers, right? And the concept of divisibility here is also very important in number theory, and that's something that we're going to focus on in particular for the first two videos here, okay? So before we take a look then at a formal definition of divisibility here, let's just quickly introduce some new notation. So to begin with here then, I think it's important that we familiarize ourselves with some new notation that we will see extensively throughout this chapter. So the new notation here then is this bar. So the way that we read this here is A divides B, okay? As you can see here, pretty straightforward stuff. Now we also have this notation here, and the way that we read this here then is A does not divide B. So kind of similar to an equals with a line for it like that. This is not equal to, the same applies here to this bar. Okay, so if the bar here is A divides B, the line going through the middle is A does not divide B. Again, I'm hoping this is pretty straightforward stuff. So for example then, 13 divides 39 as 39 is equal to 13 times 3. However, 7 does not divide 30 as 7 times 4 is 28 and 7 times 5 is 35. And what this does here then is this leads nicely to a formal definition of divisibility. So let's just introduce then a formal definition of divisibility. Now, if A and B are integers where A is not equal to 0, and B is divisible by A if there exists an integer k, such that B is equal to Ka. Now this definition here, right, this is our formal definition of divisibility. And in this case here then, we say that A divides B, and we denote this as follows. So just using our new notation here then from the previous page. So A divides B, okay? Nice and straightforward. And in the case then that A does not divide B, then again, all we do here is we use our new notation. And we write this as follows. So A does not divide B. And then finally, to finish with here, the definition provided above also applies to both positive and negative integers. So just an important point there to consider, right? So this formal definition here of divisibility is a really important definition. It's something that we're going to use quite extensively throughout this chapter. So just make sure then that you do familiarize yourself with this formal definition here of divisibility. So moving on to the next page here then, let's just have a quick look at the properties of divisibility. There are properties for divisibility that we need to be familiar with for this chapter here on number theory. So for any A, B, C that belong to the set of integers here where A is not equal to 0, then for our first property here, we say that A divides A. In other words, every integer divides itself. For the next property here, we say that A divides 0. In other words, 0 is divisible by any integer. Moving on to the next property here then, if A divides B and B divides C, this implies that A divides C. Now for the next property here, if A divides B and A divides C, this implies that A divides Bn plus Cm for all Mn belonging to the set of integers. Now for the next property here, A divides B if and only if An divides Bn for all n belonging to the set of integers where n is not equal to 0. And then finally for the very last property here, if A and B are positive integers and A divides B, then A must be less than or equal to B. Okay? Now these properties of divisibility are important, so just make sure then that you do familiarize yourself with these results. Okay? So let's just move on to the next part of this video here on the division algorithm. Now, when we add, subtract, or multiply two integers together, the result is always an integer. However, this is not the case for division of two integers. And we describe this as z being closed under the operations of addition, subtraction, and multiplication, but not closed under the operation of division. And we'll learn a little bit more about this in the next chapter on group theory. Now, the magic of the division algorithm is it allows us to find a unique quotient and remainder for any two integers. Now, if a and b are integers such that b is strictly greater than 0, then there exists unique integers q and r such that a is equal to bq plus r, where r is between 0 and b. So how does this work then? Well, we start by stating the values of a and b. We then set q equal to the greatest integer that is less than or equal to a over b. And then finally here we set r equal to a minus bq. And just note then that a is divisible by b if and only if the remainder r in the division algorithm is 0. So to finish with here then, let's just work through a quick example on the division algorithm. So to finish with here then, let's just quickly work through one example on the division algorithm. So all we want to do here then is use the division algorithm to find integers q and r such that 94 is equal to 13q plus r. So what do we do here to get started then? Well, don't forget here to begin with, all we do is state the values of a and b, okay? And we can see here then that a is equal to 94 and b is equal to 13. So for the next step then, what we do here is a divided by b. So a then is 94, and we divide that by b, which is 13. And as we can see here, then we get 7.23076, so on and so on. So in that case then, q here is equal to 7. And then finally, all we need to do here is find the value of r. So r here is equal to a minus b times q. So what we get here then is 94 minus 13 times 7. Once we evaluate that, we just get 3 here, okay? And in that case then, by using the division algorithm here, we found integers q and r such that 94 is equal to 13q plus r, okay? And as you can see then, actually using the division algorithm here is pretty straightforward. So in terms of an introduction here to the division algorithm, that gives us everything that we need. So to finish with here, all I'm going to do then is just work through one practice question on the division algorithm. So to finish with here then, let's just have a go at this one practice question on the division algorithm. Now I say that the question here is on the division algorithm. That isn't actually true. This question here is looking at proving one of our properties of divisibility, okay? So for this question then, we want to prove that if a divides b and b divides c, then a divides c, okay? Now, I did forget to include it with the original question here, but just for reference then, just make a note here. So a, b, and c here all belong to the set of integers, okay? So a, b, and c here all belong to the set of integers, okay? So where do we begin with this question here? What I'm going to quickly do here is just choose a different pen color, okay? Now, if we just consider then a divides b here, well, by our formal definition of divisibility then, we know here that b is equal to k times a, okay? Where k here belongs to the set of integers. Okay, so k here is just some integer. And we can also do the same then. And again, let me just choose a different pen color here. Let's just do it in green. We can also do the same here then for b divides c, okay? Again, by our formal definition of divisibility here, c is equal to L times b, where L here, again, just belongs to the set of integers. Okay, like so there. So what do we do at this stage here then? Well, all I need to do here is use a little bit of substitution, rearrange, and hopefully we can prove this property here. Okay, so if I just go back to my original pen color here then, what do we actually substitute here? Well, just notice then that B is equal to Ka and C is equal to Lb. So what we can do here then is substitute B equals Ka into this equation here. Okay, so in that case then C is equal to L times B, which is Ka. Okay, so we get L times Ka there. Like so. Okay, and what I can do now is just rewrite this product here. Okay, don't forget then, the order of a product here doesn't matter. The result will still be the same. So what I can do here then is write this as A times Lk. Okay, and we know then that Lk here, let's make a note here. So Lk will also belong then to the set of integers. Okay, well, how do we know this here? Well, L is an integer, K is also an integer, and an integer times by another integer just gives us an integer. Okay, well, why is this important here? Well, what I've got then is A, which is an integer, times by Lk, which is also an integer. So this satisfies here our formal definition of divisibility. Okay, so in this case here then, this implies that A divides C. Okay, and therefore what we've done here is prove that if A divides B and B divides C, then A divides C. Okay, and at this point here, QED, proof complete. Okay, and there we have it then. So that gives us the solution to the one practice question for this video here, and that brings us to the end then of this video here on the division algorithm.